Okay, welcome back, pre-calculus students. We're going to continue our study of trigonometry. In chapter 7, we introduced the trigonometric functions like sine and cosine. And we defined them in really two different ways. One way where the input is an angle and the output is like a ratio of side lengths, right? That's the right triangle definition that we used for sine and cosine. The other way we talked about sine and cosine was thinking of an angle in standard position on the unit circle, and then giving us an output which is a coordinate, point of the unit circle, the terminal point, right? And those two definitions are consistent with one another for acute angles, but the coordinate, the unit circle definition, allowed us to kind of extend that idea a little more to any angle with, positive and negative outputs and that sort of thing. So that's what we were doing back then. But in this chapter, we're going to approach the idea of sine and cosine functions from a bit of a different angle. We've already done it from two different angles. We're going to pick a third angle here, and that is from the perspective of it as just a plain old function with inputs and outputs, right? Whatever this function is, it has inputs and it gives us outputs, right? And whether you're interpreting that input as an angle or just a number, the output can be interpreted as a coordinate, a ratio, or again, just a number, right? So let's step back from the idea of angles and coordinates, and instead just think of this as a function with inputs that we'll call x and outputs that we'll call y, right? And then what we should be able to do is take this function and graph it in an xy plane, right? And somehow graph y equals sine of x, right? Come up with a picture of that. Now, the x and the y are going to mean different things than they did back in chapter 7, because back in chapter 7, we had the unit circle, right? Oops, there's a circle. And x and y referred usually to the coordinates of points on this unit circle, right? We had this x and y coordinate system that we were looking at and talking about the coordinates of those points. Now, the x and y coordinate system over here is a different coordinate system. We're not really going to be talking about the coordinates of the points on the unit circle, but more so the coordinates of points on the graph of this function, which is a different thing. So I want you to imagine that we have two separate worlds. We have the world where the unit circle lives, and we have the world over here where the graph of the function is going to live. And there's a connection between these, which has to do with the values of the outputs and the inputs. So over here, the input, like we might have like 5 as an x coordinate. Over here, we'd have 5 as an angle. Those are the things that correspond. And then if this is sine of x, okay, then sine of 5 is going to be a y coordinate, whereas over here, sine of 5 is going to be that y coordinate. Okay. Now, so that means that for the sine function, the y coordinates are going to correspond to each other. For the cosine function, it's going to be the y coordinate over here is going to correspond to the x coordinate over here, which is a little bit backwards. That's where it gets a bit confusing. But for sine, you see the y coordinate in one world is the same as the y coordinate in the other world. So for the sine function in particular, we can do is pretty nice visualization. So here is a GeoGebra visualization. I will try to post a link to this so you can come and play with this yourself. We've got the two worlds here, and there's a little barrier in between them right there. Okay, so on the left, we have the unit circle world with its x and y coordinate. And on the right, we have a different world where we have a different x and y coordinate system. And what we're going to do is talk about plotting points, where x in this world on the right, x represents the input to the sine function, and the y coordinates are going to be the outputs of the sine function. So over here in the unit circle, if we have an angle of 0, and by the way, we're going to be doing this, assuming that our angle inputs are measured in radians, okay? So here, with an angle input of 0, the sine value is going to be 0, because 0 is the y coordinate at this point. So you see there's this like dotted line that's running through here, connecting these points together. Here we have the point plotted on the graph at 0, 0. Now what I'm going to do, come in here, mouse here, come in here, and we're gonna have this increase to some x value. And what's happening is as the angle increases, we may have to go back and watch that again. As the angle increases, what's going on is we're sort of tracking the y coordinate from the unit circle and increasing the x coordinates so that they correspond to the angle, and then matching them together with this horizontal line and plotting the point for every x angle input. We're plotting a point on the graph over here at a height y coordinate corresponding to the y coordinate on the unit circle. So let's go back and kind of reset that and do that again. Let's watch that again. There we go. So our angle is increasing here. Our angle increases as x increases, and then we're plotting the y coordinates. And this produces the graph. We can go to the left as well, off backwards, negative angles, way over here. This produces the graph of the sine function, y equals sine of x. And as you can see, it's a wave. So this gives us this connection, all right? This diagram here establishes a connection between trigonometric functions, which have to do with coordinates of points on a unit circle, connecting that with wave graphs. And so it turns out sine functions and also cosine functions and various kind of combinations of them or versions of sine and cosine, they are used to model anything that has some periodic wave-like behavior. So that could be things like waves on the ocean, or like sound waves in the air, pressure waves in a medium like water, or the mantle of the earth. You can have, and then you can also have sort of periodic cycles that have a wave-like behavior, like the seasons. Temperature over the course of the year is going to be like a periodic wave sort of thing going up and down, as well as like phases of the moon and just all kinds of other periodic things that repeat. Okay, so we're going to in this chapter be studying the graphs of the sine and cosine functions, and then we'll be doing some models that use those graphs. Okay, so I want to show you also the cosine graph. So here we have another one of these visualizations. It's the same type of thing with here I'm changing the angle, which corresponds to the x coordinate. And the red dotted line here is the sine function. So that is directly corresponding. The red dots here are exactly the same y coordinate as the dot on the unit circle. But the blue dot, the y coordinate of the blue dot is corresponding to the cosine value, which is the x coordinate of the point on the unit circle. So if we go like, pick a point like here, the vertical distance away between this blue dot and the x-axis, that's the vertical height, that's the y coordinate, that is exactly equal to this horizontal distance measured here. It's kind of highlighted in blue there, giving us the x coordinate of the point. And that's because, remember, cosine corresponds to x. So there we see the graph of the cosine function. Let's look at them side by side. Back over to Desmos. Open up a new one here. If we graph y equals sine of x, this is Desmos, by the way, always assumes that your x input is in radians. So here's my x input in radians. And y equals cosine of x. There's cosine. See, they're almost the same, but they're shifted. They sort of start in different places. The sine function starts here. It's y-intercept. Here is at 0 because sine of 0 radians is equal to 0. Whereas cosine starts up here at 1. Cosine of 0 radians equals 1. So you can see that's really the main difference between them. Otherwise, they're the same curve, just shifted, right? If you go up to this graph settings here, by the way, you can change the step size for the axis labels. So if you type in pi right here, step pi, then what it gives us here is the x-axis. It puts labels on the x-axis, which are fractions and multiples of pi. So you can really see here now something interesting about these waves. These graphs have a period, which basically means the segment of graph that you could copy paste to produce the entire thing. Okay, that shortest possible segment of the graph, basically the amount of the distance along the x-axis that you need to cause it to start repeating itself, is exactly 2 pi units. And the reason for that is because back in the unit circle definition, it takes 2 pi radians to get all the way around the circle. And after you go all the way around the circle, that's when you start repeating yourself, right? You'd come back to the beginning and start over, right? Let's see if we can. Go. Oops. Yep, wrap around, and then you start over. So that's where it repeats. So we see that repetition occurring every 2 pi units. Shift down, and then here it is repeating again for the next 2 pi units. Here it is repeating again. And that happens with both sine and cosine. They're just oscillating sort of with what we call a phase shift, because here the sine coordinates are going up and down like this between -1 and 1, and the cosine coordinates are going back and forth in sort of a different way. All right. Now that's another thing to note, is that all of these peaks are at 1, right? Because the largest and smallest values that sine can have are 1 and -1, which occur at the top and the bottom of the unit circle, right there and there. Now cosine, of course, its largest and smallest values are going to be -1 and 1 as well, and those are occurring here and here. So we see the curve bouncing back and forth between those values, and that is the range of both the sine and cosine functions. All right, there we go. So there's our sine and cosine graphs. Now the one more thing I want to talk about in this video is the tangent graph. So if we think about the tangent value, remember that tangent is given by the slope of this ray, y divided by x, and therefore rise over run, meaning the slope. So tangent of 0 should be 0. But then as you start increasing x, the tangent value is going to increase dramatically, because this slope is getting very, very large. And as the angle approaches like 90 degrees or pi over 2 here, that tangent value is going to approach infinity. And then as soon as you jump over pi over 2, tangent value switches down to being close to negative infinity. And then it increases again back up to 0. Okay, so these are negative values getting less and less and less negative. So let's look at the graph. My graph, y equals tangent of x. There we go. That's the tangent graph. And just zeroing in on this segment right here, I'm going to adjust this label so that it goes to pi over 2. I want to see negative pi over 2 and positive pi over 2. There we go. So there we go. We see that tangent of 0 is 0, right? And then as you start increasing the angle, it shoots up and approaches positive infinity right here. And that is as x is getting close to pi over 2. So that is what's going on. I reset it here. That's what's going on right there. You see, as we're getting close to pi over 2, it shoots up towards infinity. That's this behavior, right? And then as soon as you cross over pi over 2, which is, as soon as you exceed, just go beyond 90 degrees, it comes back up from negative infinity. That's right there. Just when you jump over that point where it's undefined, which, by the way, since we have a vertical asymptote here, right? If I graph, say, x equals pi over 2, that's a vertical asymptote for the tangent function. Got it there. The tangent function is undefined at pi over 2 because that vertical line you would get here, if you make the angle equal to pi over 2, that vertical line has an undefined slope. So, I mean, the ray that I was attempting to graph down here, I can't even graph it. You see it sort of disappeared. It's undefined. Okay. So, all right. So that's the tangent graph. And you can see it repeating itself. As you can see, it kind of goes like that, goes like that, and then it repeats itself. And the period of the tangent graph is actually shorter, because from 0 to pi is a segment that repeats over and over again. So its period is half the size of tangent of sine or cosine. Because of course, if you go from here to here, that's all of the angles, or that's all of the slopes, right? This is all the positive slopes, and here's all the negative slopes, and then you repeat with all the positive slopes and all the negative slopes. So the repetition starts over when you hit pi. You don't have to wrap all the way around the circle. You don't only have to wrap halfway around the circle before it starts repeating itself. So, all right, there we go. I think I'm going to step back now in this video, and in the next one, we're going to look at the sine and cosine waves and break them down with some vocabulary before we start doing transformations.